Good. So yeah, now it's time for the first keynote at the first AutoMLConf, and it's my pleasure to introduce our first speaker, Alex Smola. He is a distinguished scientist and vice president at Amazon Web Services AI, and also a co-author and co-editor of several books, including the recent A Dive into Deep Learning. I'm really excited about the topic he's going to talk about because AutoML systems really combine the latest research in machine learning and also AutoML, and of course also engineering expertise. And he will talk about the recent advances of Amazon's AutoGluon tabular toolkit, with which he and his team pushed the limits of AutoML systems for competitions and also the AutoML benchmark. So please enjoy the presentation, and we will meet again afterwards for the discussion.
So first of all, welcome to this conference, and many, many thanks for organizing it. Secondly, well, I'm just the speaker. The real heroes are actually sitting in the audience, so at least some of them. So Nick and Alex, they are the two who actually started AutoGluon in Amazon, and then, I was very impressed and decided that this would be something that we should be investing in quite significantly. There's terrible echo here. I hope it's not so annoying for you guys. In any case, here we are. This is now version 0.5. This is about the 2 years journey since we started with this, and I wanted to show you a little bit how we got there, where we are. This is an open source project, so this is also an invitation for anybody who wants to participate to join in. It's all under Apache. We're more than happy to share. And it's a little bit different and weird from, the usual way of doing AutoML. So buckle up. So TLDR, and I guess this is kind of like bringing coals to Newcastle or Nahatin, is like, well, stop using XGBoost and other Earth and ResNet, just use AutoML and be done with it. And the reason for that is really because ultimately, for a good idea to work, you only need to really implement it once. Once you've implemented it and you've made it really robust, then everybody can use. And this is, to some extent, what reproducibility in research is meant to do. And, well, we're trying to get there, or at least make a little bit of progress with AutoGluon. Why are we doing this? So Andy Jassy last year said that Amazon was going to hire in the order of 50,000 engineers in a year. Okay. So by now, Amazon probably has over 300,000. But the point being, this is way more than what the supply in machine learning competent people is that's being, if you will, being produced per year. So there are maybe between 400 and maybe, if you squeeze a lot and squint a lot, maybe it's 1,000 PhDs in North America annually being trained. And if you look at CS undergrads, well, that's around 30,000. If you then add engineering disciplines and so on, maybe you get to 50, 60,000. But what you can clearly see is that, demand is outstripping supply, and it's likely to stay that way for quite a long time. So this is a problem, right? Because there are just not enough people who can build good machine learning models that are there to solve all the machine learning problems. And so the only way to fix this is to make it easier to solve those problems. And I think we've made very significant progress. So in 2012, when I taught basically a scalable machine learning class at UC Berkeley to PhD students, implementing a large linear model with logistic regression was probably the hardest assignment that I gave them. And they struggled. I mean, they got there, but, this is a good university, but that was that. So then, likewise at CMU. So then in 2017, with deep learning frameworks, well, it's kind of straightforward to implement a computer vision problem, and you can do that for a PhD level class, and the students will get it. And then in 21, well, you can essentially build some NLP competent system, and you can tell undergrads to do this, right? And we did this in Stanford, and again, the students actually got to a reasonably good point. Now, the kicker, of course, is that by now, even a 16-year-old high schooler can build a time series regressor. How do I know? Well, my son is 16 years old. He needed that for a project, and he's by no means a machine learning expert. He asked me, Papa, what's the difference between linear regression and logistic regression? And I'll just leave it at that, because that tells you a little bit, his skill level. He's okay in Python. He knows very little machine learning. And still, I basically threw him into the deep end. I was like, okay, fine, I'll show you what Conda is, and we'll do, we'll set it up and we'll do a pip install. That's as far as I helped him, and then he got it to work. So is this the best use of machine learning? Absolutely not. But the fact that he got it to work and it didn't fail, and he didn't estimate 50 times, tells us that the skill requirements that are needed to run and build machine learning models by now have actually decreased quite a bit. Right? Is this as scalable as what a PhD student can build? No, of course not. But it's acceptable. Now, what machine learning users really want is they want fully wrapped systems that do something. And unfortunately, this is what the machine learning community is building. I mean, not so much here. This is the AutoML conference after all, but hey, we're all engineers, right? We like to dive deep into very specifics, into very specific components, because engineers do that. I mean, guilty of the same crime here. And then you just tell the user, well, you go and select from those various components and you're happy. Well, this is really what we should be building, right? Don't fall asleep inside your Tesla. It's not healthy, but basically you want systems that are fully automatic. Right? So let's look at how far we've gone. And it's a little bit the glass half full, half empty story. So in 2020, when we compared AutoGluon to others, it did fairly well. And I don't need to go through the specifics, but the key point is it did better than the best of all other alternatives together, and it was pretty resilient against failures, because it did AutoML in a very different way from what everybody else did. And we'll delve into this in a moment. It had one failure, though. By now that failure has been squashed. And there's a reason why it's so hard to make it break. 2022, well, it improved further. There are a couple of other toolkits that have come up. So, for instance, MLJAR is actually doing a really good job, not the least due to the fact that they actually, read our paper, looked at what we built, and then they adopted some of the same ideas, and it got them quite far. So they did a good job. Still, we win quite a bit. So, for instance, if you look at the 1 hour constraint, then, we are the best in 78 cases, and it works quite well. So one important thing, if you benchmark AutoML tools, make sure you look at least for a minute at the flags and the call signature of the tool. Here's why I'm saying that. Different tools have different default settings. So, for instance, our default setting is not the very highest quality, but to have a trade-off between quality and speed, right? And if you have one toolkit that optimizes for the very highest quality at the expense of a lot of speed, and another one that's optimizing for a lot of speed and lower quality, and this is not an apples-to-apples comparison, right? So make sure that you incorporate both runtime and accuracy and quality settings into it. So just spend a minute or two. If you've read the paper, you can look at that too. That will help you debug benchmarks. I'm saying that because we ran into this issue in the past. So what improved. Well, we basically pushed things onto GPUs. That gave us a significant speed up. We used Ray. It supports a lot more things, and we'll dive into this in more detail. But this is just a little bit where we are. This is probably the slide that should convince everybody that AutoML is really what you should be using. So this was data we took from a Kaggle competition. This is a historical competition that ran in the past. And the idea is really, you want to see how well does an AutoML system do compared to humans, right? And Kaggle competitions have the nice benefit that people want to win them. And they want to do well quickly. So what we did is we tracked the 10 best teams. And this is over a period of about maybe a month and a half, 2 months. And we looked at, how quickly those teams improved. And in some cases, the kernels were shared. In some cases, they were not. But basically, you can see all of those teams, start off mediocre and they get better until they get really good. And at some point, they cross the 0.4 threshold. But that takes them quite some time. And those teams probably spend serious time on it. So I think it's a reasonable proxy for what you would be doing if you had to solve a machine learning problem for real in a company or somewhere, or for some medical diagnostics. And so you would probably try to do a good job along those lines. So now the important thing is, this is where AutoML gets you within 4 hours. Right. Now, this isn't the best solution. I mean, we got to rank number 14 here, right? So it's clear that you can beat an AutoML system with a lot of human ingenuity. That's not the point. But the point is, this happened after 4 hours, whereas otherwise you need to wait almost 2 months. Now, what can you do with those remaining 2 months? Well, you can start with this as an initial solution, then start improving it. So it's an easy cheat to get a jump on how well you can do by adding human ingenuity to an AutoML system. So the way that we've designed it is it's batteries included but removable. In other words, if you have your own custom models, your own pre-processing and so on, yes, you can do better. And in some cases, with gentle tuning, you can do quite a bit better. Okay. So here are a couple of other benchmarks and competitions, and this is really just to give you an idea that it does actually work fairly well. The key point in all of those cases is we didn't tweak a thing, we just used 3 lines of default code. Does it always work as well as this? No, it doesn't. So this is a little bit cherry-picked, but this, I hope, gets the idea across that by now AutoML systems are quite performant. They're quite performant, comparable with human performance, and thus, you can easily go and, use them for, production purposes. So, yeah, those are the infamous 3 lines. This is, a nice result by Peter Gisbert. And he did a fantastic job because I hope I am not mispronouncing his name. Is it Gisbert or Geisbert? Geisbert. Okay, so thanks, Peter, for doing this. So he compared a lot of different AutoML systems and essentially looked at speed and accuracy. And, there's a trade-off. And so if you look at those 2 red arrows, this is the same AutoML system as AutoGluon version 0.5.1. And if you want to get something that's a lot faster, then you pay a little bit in accuracy. This really depends. I mean, if you're detecting cancer, well, you want to be, as high as possible. And if it takes you 5 minutes to produce a result, you don't care. If you have something that's maybe running on an embedded device in the field, speed matters, right? But the key point here is really that, AutoML does fairly well. What you can also see if you look at the 3 dots on the right, is how it has improved over time, right? So the 0.1 version is more or less on par with the 0.5.1 version, except that this is on the fast setting. And you can see that one of the big improvements to 0.3.1 was accuracy with a bit of speed, and 0.5.1, again, with a fair amount of speed up. Mind you, this is log scale, so these are meaningful accelerations. So again, thanks, Peter, for doing this. Now, this looks all really good, right? Are we there yet, right? And this is, I think, where things get a little bit more tricky. I don't think we have even scratched the surface. So let me just quickly color things to give you an idea a little bit of what I think by now we sort of understand, and also where I think we need to dive into a lot more detail. So in terms of the modeling, well, model selection, tuning, validation, I think this is reasonably well understood. And I think the best paper prize paper from this conference also, makes meaningful progress towards that. In terms of monitoring, I don't think there is much integration between AutoML and observability there yet. I don't think it's like a really, really hard technical problem to pull off. It's just that somebody actually needs to build this, right? Why do we care? Because the target audience of the people who will afterwards, use those systems will probably not have the technical skills and sophistication to understand what the distribution shift and a concept and a covariate shift and a label shift and a drift and anomalies and 10 other things are, right? So observability, I think, is quite crucial. Pre-training, I think we are making some progress. So for instance, by now, 0.5.1 pulls whatever you want from, essentially Hugging Face and Tim and a lot of other models who's in. So this way you can start off by taking advantage of your fancy foundation model. I don't think we're quite there yet in our ability to use very large foundation models by now. I mean, we top out at around 1 to 2 billion parameters. Would be nice if we could do 10 to 20 billion parameters on a single GPU. That's coming, but not quite there yet. And yeah, we don't really have good tools yet for something like Bloom. It's also really expensive, so we'll have to see whether this is something that our users/customers actually want. In terms of data analysis, so I think AutoGloon is probably one of the better tools for pre-processing. So if nothing else, just take that pre-processing library and reuse it. And if you think it's broken, send us a pull request and fix it. But this is it's open source, so feel free to share. What I think we're still doing a really poor job at is all the data discovery. And so if you go to Kaggle and look at your regular competitions, you'll see that in many, many cases, the data doesn't come neatly pre-formatted as a table or something, but it's a couple of data sets, a couple of tables, and then the first step is to actually rely on some of the ingenuity of the statistician modeler to really perform the right joins, to find out what the types are, how they relate to each other. And for humans, this is all very obvious. And for an AutoML system, it ain't obvious yet. So this is something that I think we could do a lot more. In some cases, if you have a data lake, you may not even know exactly what the schema is, and you need to infer the schema of your data. Yes, it sounds crazy that people would dump data into a data lake and then not bother to actually describe it, but they do. Annotation tools, likewise, I think there's a lot of potential. So, for instance, if you if you think about it, now that you have, a workable AutoML tool, how do you actually then combine this with an annotation mechanism? It's because now the entire product is not just the labels or not just the model, but it's really the combination of both. And with that, I think you can make quite a bit of progress. On the system side, training, yes, I think we could and should become a lot more robust. Right now, it's okay, but doing this at scale predictably, maybe integration with EKS would be nice. Inference, likewise, visualization, some of it is there. Basically, a lot of the automation there, the MLOps side. Again, a lot of the people who need AutoML are probably not MLOps experts. They will benefit from it. And then lastly, people like to solve real problems. And what that means is that they will do that rarely on their own, but they will work with others together. They will discuss solutions. And I think that entire collaborative aspect is still improvable. I would say right now, this works through GitHub, or you go on Colab, or you maybe use SageMaker Canvas, or maybe you use any of the other collaboration tools that are out there, or you throw it into weights and biases. All of those things are okay, but they're not great. Being able to do this well, it's not really strictly speaking an AutoML problem, but it's still a problem if we want to bring machine learning to everybody and thus make it more automatic. You will probably need tools. So imagine if you were to teach machine learning in a high school, right? You would probably want to have mechanisms where students and teachers can, to some extent, work together. Teams can work together without having to, get an advanced degree in systems administration of a Jupyter Hub cluster, right? Can it be done? Yes, but so far there's still a lot of friction. Anyway, this is the glass half full, half empty, but it, I think, paints a very convenient picture of a lot of the things that are needed to really get us to ubiquity in machine learning. Okay, so with that, let's actually accelerate a little bit and dive into the technical parts. Tabular basics. So essentially, why does AutoGluon and Tabular work the way it does? And it really combines four aspects. One is bagging, the other one is stacking, assembling. We basically throw everything but the kitchen sink at it. And in the end, we combine multiple modalities. So let me walk you through the pieces. Bagging. So everybody knows K-fold cross-validation. That's kind of a straightforward, easy thing, right? So, you leave part out, you train on the rest, and then you look at how well we do. And then you use that for error estimates. You tune the model, and then you say, well, parameter 42 is exactly the right value. And then, oh joy, now you run it on the full data set, right? So basically, now that we know that the regression parameter has to be 42, what next? And the problem is if you just throw away anything that you've done so far and then we train on the full data set, you don't even know whether the model will even converge, right? It may have worked perfectly fine on the 5 splits that you've done before, but once you combine all the data set together, your model may diverge. Does it happen often? No, but it does happen. And so you have a problem, right? The better solution is to use bagging. In other words, we already have those partial solutions. They're slightly different, so I just aggregate them together. And I've killed two birds with one stone. First of all, I don't have to do any extra work. Secondly, in order for the system to fail, all 5 splits in this case would have had to fail in order for the system not to produce a meaningful result. So it's more robust, both statistically and also in terms of systems. You also get a little bit of, variance reduction and so on in the net, at test time, because you have a number of solutions. You could almost view them as, draws from, the version space. They're not independent, so it's not like what a good Bayesian would like, but it's better than nothing. So now, if you have something like a deep learning model, then, well, this doesn't quite work so well anymore because it's really expensive, right? So if you have 2 billion parameters and you have 5 folds, well, then, you get 10 billion parameters. But it turns out that if you average in parameter space, then in many cases, this is not so stupid. And this was invented twice, once called swag and then reinvented later and called model soups. And it's the same idea, more or less. But model soups sounds cooler, so more people cite that, but swag was actually earlier. In any case, so you can do this. Now, the next thing is after we've aggregated over multiple solutions for the same model, well, can we do more? So one thing that may have happened to you in the past painfully is you built a nice model and then somebody said, what about k-nearest neighbors? And then it turns out that k-nearest neighbors actually works better. Doesn't happen very often, but sometimes you get embarrassed by it. So why not add this as well? And in some cases, why is it a good idea? Well, it's non-parametric and it's quite robust, right? You can use trees, and in some cases, you get embarrassed by trees, right? Or forests, right? Again, robust and all of that. So, for instance, if you follow Bojan Tungus on Twitter, I think every third tweet of his is XGBoost is the answer to everything, right? And it's a really good algorithm. So, why not use it? Then there is by now a lot of literature on how can we beat the evil XGBoost with a deep network, and we're getting there, and the models are getting better. And so, yes, okay, sure, you build something with basically the best of, the 21s and 22s. So in other words, residual networks, by now even transformers are making their way into those network designs. And, well, why would you not take advantage of it? Right? And so what you end up with is you basically have this plethora of models, and most people will go and say, well, okay, now that I have this plethora of models, well, what should I do, right? Let me actually perform hyperparameter optimization. And now it's a big optimization problem over maybe 10 different model types, over maybe 5 model parameters for each of those. These parameters are different because, you don't need to define what dropout means for XGBoost, and the number of leaves doesn't mean anything for a transformer, right? So you get this very complicated search space, and you can spend a lot of time building a lot of models to try and find the very best model. But that's actually not really what works so well. And I think we should have wisened up to that at the latest after the Belcore the submission, and that was the prize-winning submission for the Netflix contest, right? So this was a throw everything but efficiency added approach, which combined fleet and methods, factorization, and a lot of other things. They were very sophisticated the objective functions, but in the models, they just took a lot of things. And quite honestly, when I read that submission, initially I wasn't really discussing. This was very exactly that kind of let's find that one true pure model that solves it all, right? And it was like, hey, they implement everything. This is cheating, right? Turns out this actually works really well. And well, essentially the reason is because quite often reality doesn't happen to do you the favor that it's nicely described by any one of those models. But you are much better off combining multiple things. In other words, we take all those models, we train them, and then rather than trying to figure out which one's the best, we just take a combination and use a subset of the things that by now make its way into AutoMLConf'. And if you have something nice, well, we'll happily take that too, right? So by all means, talk to the gentlemen in the third row, and if you have a nice algorithm, yeah, join us, right? This is like the board. One of the important things is for practical solutions that if you go to a user, they can bring their own model as well. So why would you do this? 2 reasons. First of all, usually when people start, solving problems, they're not stupid. They come up with a good solution for their problem, and it'll produce possible or good results. And then you walk in and you say, "I'm the new AutoML system. I will replace you." And in some cases, this will succeed, but in some cases, actually, our solution will be pretty good too. And it would be very wasteful to throw it away. So why not just add that custom solution to all the rest of the models? First of all, the outcome is better. Secondly, it gives the users a higher sense of ownership because they don't feel like they're just being replaced, but they're now getting more powerful tools that complement what they have. So this is both an engineering and a psychological reason why you really want that. It also makes it really easy for us to add new models. So what's the statistics of the math behind why this may be a good idea? And so what I've done is I've just, sketched out 3 models, A, B, and C, and, for some regularization parameter, you get more or less powerful models. This is the nice case where you have, something convex, and then you have nested function classes, yada, yada, yada. So this is Tikhonov and regularization, VC bounds, nested function classes, and all of that. Neural networks aren't that nice, but let's for the moment presume we have 3 of, those models. And they all have a very different view of which functions are simple. Right? Because, well, you implement something and certain things are simple in that stratification and not in another one. So you can, keep on, increasing the complexity. And if you have something that's truly non-parametric, eventually, no matter what your problem is, your model will cover it. But the issue is, if, reality is a little bit different, well, why not do the following thing? Let's take a convex combination of all those pieces. That doesn't actually cost you that much in terms of model complexity. It's basically just the log of, number of models, right? So we see dimension-wise, it's not too terrible, the increment that you pay. And now you have the convex hull of all those models. And that gives you a much safer bet that your solutions are close to what you really are trying to solve. So that's as much of a mathematical theory as you're going to see in this talk. So don't worry. Okay, so we have bagging, we have assembly, and now let's look at stacking. And stacking, again, is a really old idea. So, for instance, William Cohen did this, as an alternative to all the max margin Markov networks and so on. And the idea is very simple. Well, you basically go and, take, train your models, then you could do exactly what I just described. You bag over various folds, you aggregate, different models, and you call it a day. But what you could also do is you could just say, well, let's actually take the predictions that this first battery of models has produced, and then, well, use these as inputs for the very same models again, right? And because, the outputs will actually have produced very good features, and maybe the output of the decision tree is a really good feature for the deep network, and vice versa. And humans do this, right? So, for instance, when you do model aggregation for, epidemiological forecasts, you might say, well, this model works well in this region and that model works well in that region. And then you somehow figure that out based on the covariates and you combine accordingly, you get something good, right? So humans do that quite often in practical cases. So why not let our models themselves take care of it? Alas, there's a tiny little problem. And the tiny little problem is, as you can immediately see, well, you may end up overfitting. Because if I train on that label and then I use the prediction to train on that again, then potentially I get horrible overfitting. And I'll show you in a moment how this can be ameliorated. But if you just look at it, basically, you take, and so just bear with me on that overfitting part. But essentially, you take the input, you get those various models, you combine it, and then you apply the models again, you weigh, and you generate the output. What this does is it looks very much like, your favorite deep network, especially. So let's say this looks very much like a dense net design or a ResNet design, where you go and just, input features in the first layer that it produces, x1 is, x, and then f of x. The second layer would be x2, would be x1, and then, the next function of the input, and you keep on doing this. Now, there's a bit of a problem. And the problem is, I said, well, you might end up training on the labels. Right? And that's not very good if you use your labels as features. But again, backing comes to our rescue here. Namely, what happens is, well, let's take, fold one. Fold one is missing, this blue data set. And so, therefore, the predictions that, fold one makes on, the, validation set one, those are independent of the actual labels conditioned on the covariance. So you get a conditional independence between predictions and labels on fold one. For fold two, the same thing holds for the predictions and 3 and 4 and 5. Now, one little thing that I didn't tell you before is actually we oversample a little bit here. So if we have, let's say, 5-fold cross-validation, we don't just take 5-folds, but we oversample to have 10 or 15. But in any case, what this now means is that at least for the second level of the stacker, the output of the first level is still usable because I'm going to use, the predictions for fold one as features for fold one, predictions for fold two as features for fold two, and so on and so on. And so this works at least one time. Unfortunately, if you wanted to add a third level of that stacker, you will get some dependence leaking through because now you've basically used, let's say the labels for fold one to get, something for fold two, which then makes its way back into fold one. So you could split it in by having something that's nested, but that just makes the entire algorithm run very slow. So right now, this is a little bit of an open problem. So you can have an good idea for it. We'd love to hear about it. Right now, what actually happened is that the 0.5 release went back to only 2 levels of stacking from 3 because 3 levels did not reliably improve accuracy as opposed to spending all the compute time budget on 2 levels. I didn't go into any of the considerations as to how you use the compute time. Suffice it to say, given that you have 2 levels of a stacker, given that you have multiple base learners, given that you have multiple folds, you can use that to prioritize what to train and how far you go and how much time you spend. And also given that you can oversample. So there's a nice planning and optimization problem there to make use of a given amount of compute time reasonably. I don't think we do the very best job we can, but I think it works reasonably well, as in we usually stay fairly well within our compute budget. Anyway, so this is essentially why the stacking actually works. Here's another example. This is from 2 years ago, and this is how to do on accuracy normalized at 1. And anything to the right is worse, anything to the left is better. And most of the colored diamonds are to the right. So they're different AutoML systems. And there were a couple of cases where we performed a lot worse. So for instance, for shuttle and KR versus KP, by now those numbers look a little bit better. So now I mentioned a little bit the, how to spend time and how to budget it. One thing that's clear is that, by, throwing more models and more folds at it, you get high accuracy. And what we did is we compared AutoGlue on 1 hour versus 4 hours, and we did the same thing with GCP tables, H2O, and other tools. And we wanted to see whether, giving the systems more time actually improved stuff. There's no guarantee. And, there are some cases where for instance, autoglue on 1 hour. So in this benchmark, there were 38 cases. And in 5 cases, the 1 hour result was actually superior to the 4 hour result. I mean, this can happen. But it happened for us less frequently than for others, just because bagging is a wonderful way of sinking a lot of compute into it and getting more accurate numbers out of it. There are a couple of other pieces of ablation here, and I'm going to skip over that because otherwise I won't have time anymore to go into the more recent stuff, namely fusion. So this is the one thing that most people miss when they talk about multimodal data. They assume that they have an image and a caption, or that they have a movie with a transcript, and then they have maybe a video, audio, and transcript, right? But that's not what your average user has. Your average user has something like this, right? This is, I searched for fusion on Amazon, and this was the top hit. Yeah, these are good razor blades. So you have images, you have title text, you have some numbers, you have some more numbers, and you have some images, not just one, but in this case, it's actually 7 images. And then you have some more text, right? And then, I think there's also some tabular data. Yeah. Okay, I forgot to actually annotate this, but right, this is some random tabular data stuff, and in our backend there's a lot more of this stuff. So this is what real data looks like, and not all fields are always populated. So what are you gonna do? So basically, you want to combine all the data for a good model, and usually you have product teams or whoever solves the engineering problem, and they spend all their time on then trying to figure out how to combine those various sources to produce a good outcome. This is where most of the engineering time is being sunk. And it's also job security a little bit, but that's a separate story. So essentially, what's happened more than once is we've gone in and said, okay, let us help you. And then, we got results that were superior to what other teams have been working on for, many months, sometimes years. Now, you might wonder, does that mean that, we are so much smarter than everybody else? No, absolutely not. What it means, though, is that, we've optimized and integrated every single component and done it once or twice. And then you can automate this thing, right? So basically, this is exactly the idea of, build once, deploy everywhere, as opposed to try it out everywhere manually. So if somebody has to manually implement K-fold cross-validation every time, then that's a lot of the engineering time gone for no good reason, right? So, for instance, right, so text embeddings, what's a good idea? Well, you take, a couple of embeddings, then you look at, for instance, how exactly you aggregate it. Turns out that certain way of exponential decay is a good idea. Or then, how do you choose fuse things, right? I mean, again, you want to try it out, right? So you can, for instance, throw everything at a transformer and you turn everything into text, right? You could do that. Or you could just have, an MLP for the categorical and something else for the numerical parts, and then a transformer for the text. Or, you just, throw pieces at it and then. Right? So there's a lot of different versions, and I'm not going to bore you with the very specific details. But the thing is, this is where a lot of teams spend a lot of time. The fortunate thing is that there seem to be some general patterns of what works and doesn't work. And so you try it out and then you deploy it multiple times. So once you have that, we again apply our stacking trick because, why not? Except that, no transformers allowed at the second stage, right? Basically, a foundation model wouldn't do very well there. But at least then you can do better than what your plain deep network would do. Let's look at some progress that we've made. So when we released it in the version 0.1, it was quite an upgrade over the the prior 0.0.15 release, so 70% win rate. We added multimodal and text. Fast AI produces really nice tabular deep networks, so yeah, why not? And we added XGBoost. XGBoost doesn't always work for categorical variables, so that's why there's, for instance, cat boost, but there are some other ways to fix this. Then point 2, got a little bit better, but a lot faster and used a lot less disk. And then, thanks to NVIDIA, we got NVIDIA Rapid support. So now you could use your GPUs. And mind you, the GPU implementations of some of those algorithms aren't always quite the same as the CPU version. So you have to be a little bit careful. Then point 3, again, a little bit better, but a lot faster, especially for inference, because a lot of our customers told us that they want fast inference, not just want, they needed it. This was a requirement. Otherwise, they couldn't even work with it. We added text and image support, PyTorch model through Tim, and the ability to add custom models exactly to address the issue that, if you have a team that already has a solution, you want to be able to take advantage of anything and everything that's already out there, right? So the goal is not to replace, but to absorb, just, I guess, like the Borg. Point 4, again, quite nice increase in win rate, especially at scale. Why especially at scale? Because if you have something that's a lot faster to train, then it wins a lot more because you can try out a lot more things. Ray support helped. In some cases, between 80 times faster inference speed and 100 times less disk usage. It's not a typo. More constraints, Windows support, basically. And then, because at that point, SageMaker started to realize that this is probably something useful to integrate. It's now available in SageMaker. So if you want to use an AWS SageMaker and have a good AutoML system, you can do that through the deep learning container in there. 0.5.1. So 0.5.1 came out last week. 0.5 about a month before. Part of the reason for 0.5 and 0.5.1 was 0.5 coincided with remars. And so we hurried very much to get something there that, my manager could show on stage. And then 0.5.1 has documentation, a lot of the other goodies in it. It's not a bug fix, but it has a lot more documentation and support material. And by all means, please go to GitHub to read the full list of all the people who worked on it. It's a lot. Some of the key parts are time series support, and you're going to see a lot more on the time series side over the next year. So far, it's decent. Give it a year and it'll be great. A lot more support for fine-tuning for multimodal. So the issue is basically if you have a monstrous model that is a couple of billion parameters large, then an AutoML system that needs to run in a couple of hours will probably not succeed at training such a large deep network. At the same time, those deep networks actually work really well, so we want to be able to take advantage of it. And the way this can be done is by looking at small modifications of an otherwise already pre-trained system. Small modifications are basically stuff like only change the bias terms, or only change the scaling terms, like this is norm fit, or LoRa, low rank. If you search for LoRa, you get antennas. So this is a terrible name, but the paper authors decided to name it this way. It's basically just make low rank modifications to the large matrices in the transformer. Right? Why? Because this way you can train and fine tune those models on a single GPU. you might ask, why on earth is Alex proposing this? Because after all, AWS is in the business of, providing you lots of GPUs. Well, sure, but sometimes maybe a user may try that on their machine at home, or they may be frugal, right? So it matters. Tabular now has transformers in it. We have more data augmentation because, yes, why not? So a lot of things, quality of life improvements that otherwise you could do manually, now are starting to find their way in it. And it scales up to basically 100 gigabytes. So to give you an idea, this is some cat prediction task, right? Will this cat be adopted? Well, okay, you be the judge. But okay, fine. So you take Hugging Face embedding, flip embedding for the text image, and then we have another pre-trained model from Tim. We combine this all with the tabular data, and it does a decent job. So 20 billion parameters is where we want to get to. I think I'm pretty much out of time because I need to probably leave a little bit of time for questions. So tuning the accuracy, well, there's still a bit of manual pieces in there because, Hugging Face has so many different transformers, which one to pick. This is the part that I think we can probably get better at automating. But this is a very dynamic area because people come up with new models every day. So it's probably going to be a never-ending story there. But if somebody has a nice idea on how to automate this, we'd like to know. So what can you do? Well, if you, do a little bit of gentle tweaking, namely, take 3 different embeddings, and then, this is actually, Kaggle Pet Finder. I think this is a live competition. And, Xinjian managed to go from, I think we were at, top position 30 or so. We're now 20 out of 3,000. And this is by now a little bit cheating. It's not fully AutoML anymore because it's really taking, a couple of embeddings and then combining it. So this is both impressive where Xinjian has gotten with a small number of codes, but lines of code, but it's also unfortunate because it's no longer just, set, fire and forget, right? Ideally, I'd like to get to a really, really good position without the need for human intervention. But it shows you that it's batteries included but removable. So if you want to customize, yes, you can do it. Okay, I think we can skip this. Yep. Forecasting, likewise, by all means, look at the description. Quick commercial break. So actually, this aligns very well. So hyperparameter tuning. So right now, well, we don't really need it. As a matter of fact, we pretty much kicked out the HPO tool from our partner team in Berlin because it had a lot of dependencies in it and it made installation more complex because more dependencies just impose a higher burden on the user. That's it. Once you actually go to large foundation models, you may need this back. So, well, something will be coming back there. And Fine-Tune just released their 0.3 version. And so this actually aligns nicely with their price. So this is basically the short ad. Now, do we need help? Absolutely, a lot of it. And basically, what's our plan for the future? Well, it's really more of everything, covering the various pieces, anything from data ingest to GUIs to visualization to problem detection to better multimodal support. I mean, we're currently working on it, but I think this is really where a lot of the action will be. The entire labeling, annotation, model building there. So Label Studio or similar integrations might be a good thing. Fairness, right now, nothing's there yet. Would it be difficult to add? No. Would it be difficult to add something that does no harm? Yes. So it's very easy to come up with a fairness tool that satisfies whatever criteria, and then say, well, we now have fair AutoML, right? But being able to show that this does not actually make things less fair effectively is a lot harder. And this is one of the reasons why I'm a little bit hesitant. Will there be fairness diagnostics? Most definitely. How much we fix automatically, I think, is a separate question, because we don't want to harm people, right? Explainability, causality, yes. So, for instance, feature analysis and so on, pieces there are coming. We need to scale further. 100 gigabytes are good. A terabyte is better, right? 10 terabytes are better still. Speed, we always want more. Larger hardware support. Online prediction endpoint, this is going to be a big one. A lot of work to be done. Let's see when we get to that. Talk to me offline if you're interested in helping. And then, even more foundation model integration. I think we've, again, just scratched the surface of what can be done there. So with that, I think I'm exactly at time. Let me skip through this. This is the most important slide. These are the people who did the actual work. I'm just here doing the talking. And they really worked hard on it. Okay, so with that, thank you very much for having me here.
Okay, thanks for the great talk, and let's have one or two questions. And we need to swap, because apparently that's the better one. Okay, there was one. Yes, over there.
Does AutoML give out barrier frontiers? Like, can I tell it, give me the barrier frontier of all models with this many to this many millisecond inference time on this hardware? Whatever it's hardware agnostic, but it's just a CPU.
Well, it does some of it, and you can adjust also, how much time you want for training. For inference, so there are pieces that can be done. I think Nick is going to walk into a lot of detail there.
Predictor.leaderboard, Pareto frontier equals true. It will automatically compute a series of ensembles, combining all of the models in a way such that you have inference latency actually trade-offs across all of the ones that you've trained is ensembled together optimally. There's also infer limit at at fit time, where you can say this is how fast I want it to be, and then it will just automatically optimize during training the final model to be that speed.
One quick question. So you showed that for the low time limit on the good is particularly great. When you have more time, there you don't have HPO, and so you're not benefiting from more time as much as other tools. What are your thoughts on how HPO or other things could be integrated? So what would you do if you actually have a case where you have more time?
Well, it does benefit from it, and it still is better than the alternatives. And so, for instance, if you look at GCP tables, we actually did something that was, let's just say, extremely favorable to GCP tables, because GCP tables invokes 64 instances, right? And we counted the 64 instances of 1 hour as 1 hour, right? So, in that sense, yes, it does improve. Now, what would you do if you had more time? Well, there's a lot of parameters. So, for instance, you can go and say, well, I want to actually then run distillation to be able to, have a model that's really fast at inference time, right? That's, I think, a very reasonable constraint. You might say, there are some areas where you need HPO. So, for instance, what I alluded to, once you go to the foundation models, well, probably you will need some of that to, do less poorly. The other thing is, for instance, when you may want to use HPO in a slightly wacky way, insofar as you want to run HPO to tune your defaults for AutoGluon over a large benchmark suite. Now, if that benchmark suite happens to be a set of problems that are similar to the ones that you want to be solving, then you could probably publish this as meta learning, right? But so there are definitely ways how you can spend more compute, but I think it's reasonable to have a meaningful balance between the amount of compute and the difficulty of the problem, right?
Yeah, and very quickly, I'd like to add on to it. It's just that when you're trying to optimize an AutoML system and you have to consider all the different components, all of them fight for time, right? If you only have 4 hours of compute, you need to do all of the tricks that you have in some combination in 4 hours, right? Or 1 hour, whatever, right? And so HPO is something where it fights with resources. And at a certain point, once you have enough time, it becomes the thing to do with the remaining resources, right? Because you've got diminishing gains on stuff you've already invested a lot of time into. So I think there's still a lot of work in terms of looking into that larger time limits that where a lot of times 4 hours is not like people would want to do like 72 or something, right? If it actually matters, right? And so I think that that's very interesting. And as Alex said, meta learning and trying to improve the default configurations and things like that are very important too.
Thanks for the talk. So when you're running all these deep data cannons and SQs and so on, application sync on data, you do over thousands of data sets. Is there a sort of scope for meta learning too? Because you have all these results, all this meta data. Is there a sort of scope you think to meta learning and those like me, or do you think that this is now so designed? It's just
well, I mean, there's always scope for meta learning. I mean, as said, for instance, for the defaults for hyperparameters that you may want to choose, there's space. There's also space for specific problem groups. Not all of those base learners may actually be a good use of your time. So there's definitely ways how you can prune this. Now, beyond that, you can start, training a little foundation model. Some people have talked about maybe having like a universal, time series forecast, meta learned model, and maybe, I don't know, probably DeepMind or OpenAI will throw a couple of $1 million of compute at it and publish a paper on it, right? We may not want to spend that much money on it, but yeah. So I think there is space for meta learning. The more interesting thing would be if you could actually train on multiple problems at the same time, and you're allowed to transfer and share statistical strength between those models. This may or may not be true. So let me give you an example where if you could do it, it would be really awesome. Let's just say one of our customers has a lot of customers of their own. They have their own data set and their own problem. And it's a fairly simple statistical estimation problem. But each of them is its own entity, and they are entirely unwilling to share data across, right? Then it becomes very difficult to design a meta-learning system that can learn in any meaningful way across this, even so everybody would benefit from it, but they may not be allowed due to a lot of regulations to share the data beyond, right? So imagine this is healthcare data, then you clearly can't, right? There are lots of other business cases when this is not the case. But so that's some of the, practical constraint that meta learning sometimes runs into.
Yes, I would end this session. No? Okay, good. Do I have some time for coffee left? I would end this session. And let's thank the speaker again.
And next up in the schedule after the coffee break is the tutorials. So here is the NAS tutorial, the first NAS tutorial. It's more foundations on NAS. And the other one is over in, well, where the coffee is.